Good morning, everyone. My name is Peter Jacob. I'm the Associate Director of the Smithsonian's National Air and Space Museum, and I'm delighted to welcome everyone here to the museum for this very special press conference by NASA and the National Air and Space Museum, focusing on the next great venture in planetary science and exploration. We're here this morning to announce the landing site for the Mars Science Laboratory, and also known as the rover Curiosity, and share some of the details of what the mission hopes to accomplish. On July 1st, 1976, just 35 years ago, on the front steps of the then brand new National Air and Space Museum, a ribbon-cutting ceremony was held to dedicate the Smithsonian's newest museum. But it was no ordinary ribbon cutting. The task was not accomplished by the traditional large scissors, but by a signal sent from the Viking 1 spacecraft orbiting Mars, and just days before its descent to the surface of the red planet. It was a dramatic connection between the exploration of Mars and the new National Air and Space Museum, but it would hardly be the last. The relationship between the museum and Mars and planetary research was just beginning. And I might add that we have a Viking spacecraft on display here in the museum, and the Viking that is on Mars actually has been transferred to the Smithsonian by NASA, so we're free to go pick it up anytime we like. But I dare say that the reach of the Smithsonian's National Air and Space Museum is probably farther than any other museum in the world with our collections on another world. This museum is world-renowned for its collection of historic spacecraft and the millions of visitors that come every year to learn about them and be inspired by them. For decades, we've enjoyed a close relationship with NASA to ensure these extraordinary artifacts are preserved once they've completed their missions to expand the frontier of scientific understanding and to broaden the human experience. This partnership to preserve the heritage of spaceflight will add another milestone to the national collection with the arrival of the Space Shuttle Discovery at the Smithsonian next spring. And I'd like to take this opportunity to publicly thank NASA for selecting the National Air and Space Museum as the repository for this treasure. I can assure you that we will bring our very best stewardship to this object that represents the skill and vision of the millions of people who had a hand in its creation and fulfilling its mission. With the curation of these world-changing artifacts and the stunning buildings that house them, this one and the Stephen F. Wood-Barhazy Center that we have out near Dulles Airport, enjoy widespread awareness. But what is less well known is the Smithsonian is not only a keeper of history, but it is also a maker of history. NASA's founding director, Apollo 11 Command Module pilot Michael Collins, created the Center for Earth and Planetary Studies in the 1970s to engage in planetary research and to house mission data and imagery for all researchers to investigate, thereby establishing the dual mission of the National Air and Space Museum of both history and science. He selected Dr. Farouk Elbaz to build and lead the center. Farouk had been one of the principal scientists involved in selecting the landing sites for the Apollo missions, so Mike Collins knew him quite well. In addition to the Earth and lunar studies, research on Mars, Venus, Mercury, and other satellites have been the focus of the center throughout its 35-year history. NASA scientists have been key contributors to many historic missions and are currently involved with the Mars exploration rovers, the Mars Reconnaissance Orbiter featuring the HiRISE camera and the Charade radar, Mars Express with the Marsis radar, the Lunar Reconnaissance Orbiter with the LROC camera, the Mercury Surface Space Environment Geochemistry and Ranging spacecraft, better known as MESSENGER, and of course the focus of today's announcement, the Mars Science Laboratory. As the curators and collections care staff work to preserve the history of space exploration, the museum's planetary scientists add to the current exploration of space with their highly regarded research and participation on history-making missions. We are fond of saying around here that if it's on Mars, orbiting Mars, or on its way to Mars, NASA scientists are involved. Scientists collaborate with researchers and mission planners all over the world, and we are extremely proud of the contributions they make to the inhabitants of this precious planet we call Earth as we reach out to other worlds and strive to understand where we've been as well as envision where we'll go next. For those who are lamenting the end of the shuttle program and think at the closing of the curtain on American space exploration, they need only to look at the planetary missions currently gathering data and the next ones about to launch to know that our space program is very healthy and every day is still taking us places we've never been. Which brings us to the subject of today's press conference, the Mars Science Laboratory. We are very proud of our own NASA Center for Earth and Planetary Studies scientist, Dr. John Grant, and his role with MSL, and we'll be hearing a bit from him later. And I'd also like to point out that we have a full-size model of MSL on display in the museum at the far end, and I invite you to take a look at that after the press conference, as well as partake in the many programs we have going on today in our annual Mars Day program. We've got stations all over the museum talking about the research that our group does on Mars and generally about Mars. So with that, I'd like to begin this discussion by introducing NASA Chief Scientist, Dr. Waleed Abdelati.
Well, thank you, and thank you for hosting this event, because I love this museum. Every time I come in here, I'm a kid again, you know, looking around at all the incredible and exciting stuff. And since I've become chief scientist at NASA, I've got to even nurture that child that much more. So I think it's a great event in a wonderful venue, and I really appreciate that. I want to start just by saying, you know, a lot of attention has been given in the last weeks, months, years perhaps even, to the event that concluded yesterday with the landing of the space shuttle, the safe and successful landing of the shuttle, marking really the turning of a page to a new chapter in human exploration of space. Things change, things evolve, but what remains constant and what brings us here today to this room for this conversation is the fact, what remains constant is the urge to explore, the urge to reach out beyond where we are and understand our surroundings and our place in it. It's really ingrained in our DNA. It's at the very heart of who we are as human beings and the human spirit. So to feed that, I believe NASA is actually, well, I don't believe, I know that NASA is phenomenal. I believe the greatest agency in the world in feeding that hunger, helping us explore, helping us understand our planet, our solar system, our universe, and our place in that. And we do this in amazing ways. We have incredible people doing unbelievable things, and you're hearing from several of them today. I know 4 of you, and you are all incredible, and the 5th I'm just going to assume by virtue of the company you keep. But we have incredible people doing incredible things. I mean, think about it. Landing a rover on Mars with pinpoint accuracy at a location you're going to hear about today, and I almost wish I didn't know it because I'm scared to death I'm going to say it. You know, just blurt it out and ruin everything. But I don't think I will. But really, it's not just Mars. It's not just human exploration. This year alone, we've entered orbit around Mercury with the Messenger spacecraft, telling us secrets about the planet closest to the sun. We are launching in a couple weeks to Jupiter. We have Earth observing capabilities in place. We're looking to the far reaches of the universe. We have a very, very robust science portfolio, and that's important for a couple reasons. One is science really is one of the 3 pillars on which this agency stands. Human space flight, human exploration of space, science, and aeronautics. And to see it robust and to be a part of this conversation is really incredible for me, and I hope and believe incredible for you. And sort of with that in mind, I want to invite you, as you hear what you're going to hear in the next few minutes, I want to invite you to go back to that kid in you that looked at stars, that was fascinated. And you know what I'm talking about, because I'm sure you felt it when you walked into this museum and you saw the LEM, the module that landed on the moon. Find that person as you hear this information and sort of let that person come up inside you, informed by all the smart stuff you've learned over the years from the time you were that kid looking up at the sky and the stars and in absolute wonder. But hear what you're going to hear through that prism. And I think you'll really appreciate and feel how unbelievable this really is. I mean, we live it, we breathe it, we work it, and we are all still in awe of it. You know, there's not a day that goes by where I don't think about that rover or other activities we do at NASA and just get blown away. So I encourage you to receive this information in that spirit and then transmit that information in that spirit. Deep, deep down inside you, there's something that craves this stuff, that hungers for this stuff. And to be able to feed it, the fact that we have the technologies, the science capabilities, the engineering capabilities to deliver what we are delivering is absolutely incredible. So let's not lose sight of that. In fact, let's elevate that, because I think it's crucial. And you're going to hear some amazing things about some unbelievable capabilities, and I'm certainly excited to hear what everyone has to say. So with that as a setup, don't let me down. Thanks.
Good morning, ladies and gentlemen. My name is Dwayne Brown with NASA's Office of Communications and NASA headquarters. As you've heard, today is Mars Day, and what better venue to make the special announcement on the destination of NASA's next Mars rover. We have a lot to cover. I'm going to introduce our participants. They're going to give you an incredible presentation. Then we're going to open it up for questions. First up, Michael Meyer, lead scientist, Mars Exploration Program, NASA headquarters, Washington, D.C. Michael Watkins, while an engineer, his official title is Mission Manager for the MSL project, the Jet Propulsion Laboratory in Pasadena, California. John Grant, geologist, Smithsonian's National Air and Space Museum here in Washington. Don Sumner, geologist, UC Davis, California. And John Grotzinger, MSL project scientist at the Jet Propulsion Laboratory in Pasadena. And with that, Michael, kick it off.
Hey, thanks, Dwayne. 2 days and 35 years ago, Viking 1 landed on the surface of Mars and made the first astrobiology measurements on another planet. The landing was actually delayed because they didn't have the images to know where to land. We are in a different era. We are here today to announce exactly where we're going to put the Mars Science Laboratory, the first astrobiology mission since Viking. We indeed are in a different era in that in 1995, NASA produced an exobiology strategy for exploring Mars and laid out a series of missions of how to understand the biological potential of the red planet. Basically, it led the Mars exploration program to go from global reconnaissance to detailed measurements on the surface to the eventual return of samples from Mars. The Mars Science Laboratory is on that path and plays a very critical role in it. We've done our homework. The engineers have designed us a spacecraft that can get us to where we want to go. And the scientists have integrated terabytes of information to decide on the best places to go on the planet. And we're able to do that. In fact, we found so many wonderful places on Mars, the science community had a tough time deciding which one might be best. And so it was through a process of 5 science community workshops, detailed engineering evaluations, and a directorate program management council in which it was finally decided to adopt what the Mars Science Laboratory science team preference was and to select the site. So we are going to the mountain in Gale Crater. This is a 5-kilometer high mountain with layered terrain. It exhibits 3 different kinds of environmental settings, perhaps a trilogy of Mars history. And it's a worthy goal, a worthy challenge for such a capable rover. So to tell us about the capabilities, I will now turn the podium over to Mike Watkins, who is the mission manager of MSL.
Okay, thanks, Michael. It's great to be here at the Air and Space Museum to announce a landing site. And one of my main jobs on the project has been preparing for operations. And the landing site is a big driver in operations, as you can imagine. But before we get into the characteristics of the Gale site, I'd like to talk a little bit about the characteristics of the Curiosity rover, how it compares to previous rovers, and how those capabilities factored into the landing site selection. So if you go to the first graphic, this is our family tree here, family portrait of rovers, and they really are kind of related. They're all built out of the Jet Propulsion Laboratory in Pasadena, and really a lot of the same people worked on all three of these rovers. A lot of the same engineers, starting with the Mars Pathfinder, the Sojourner rover, moving up to Spirit and Opportunity, the Mars exploration rovers that have been so fantastically successful, and of course Opportunity is still trucking along on the surface of Mars years after landing, much after its nominal mission. And then you see Curiosity there on the right. And as mentioned earlier, there's actually this model of the rover is actually out in the hallway that you can take a look at here at the museum. Now, the progression of size, a lot of times we're asked, why are they getting bigger? And the reason they're getting bigger is because the Mars program, as Michael Meyer talked about, is a science-driven program. So you're really trying to carry more and more instrumentation, more science payload. If you go into a scientist's laboratory, you see rooms full of instruments, and we're trying to get as much of that as we can onto the surface of Mars. So we see the progression from a very small payload on Sojourner up to something like 5 or 6 kilograms maybe of payload on Spirit and Opportunity, and now more than 10 times that on Curiosity. So later on, John Grotzinger will talk about how we're going to use that payload at the Gale landing site. But in addition to just carrying the payload, we've made a lot of improvements to the landing system and to the rover capabilities that make it easier to get to better spots on Mars to do more detailed scientific investigations, as Michael Meyer talked about in the strategic plan. Let's go to the next graphic. This particular, the family portrait, of course, is a model of the rover, and this is a real thing. The rover has actually been shipped down to the Kennedy Space Center in Florida for final assembly and test. These are some images of the last testing in the spacecraft assembly facility out in Pasadena. What you see, there's a rover there on the bottom with the mobility, the wheels, the rocker bogies tucked up tight there for packaging inside the aeroshell. And on top of it is what we call the descent stage, and that's actually the kind of the rocket pack that attaches to the top of the rover that will land us on the surface after we get through the Martian atmosphere. And we'll show that in an animation later. And that allows us to actually land directly on the wheels. So we don't have a separate pallet or a separate landing gear. We actually use the wheels and the mobility system of the rover. They're actually a very effective landing system, and that allows us to both use the capability of the mobility system, as well as save weight by not building a separate landing pallet and put all the weight we can into the actual rover and the instruments. Let's go to the next graphic. Next graphic is the rover in test, and here you can see testing the mobility system here. This is the actual flight unit here, driving up ramps and making sure that we have the full range of mobility that are required. And you can see for scale some folks standing around it there. It's quite large. It's kind of car-sized and actually wider and taller than most cars. Let's go to the next graphic. The next graphic is actually an animation. It shows the entry, descent, and landing sequence. And there's a couple of changes that we have made for this mission that will really improve our ability to access the most important scientific places on Mars. One of them is we can control the lift of the vehicle a little bit during entry, and we can cancel out some unexpected differences in atmospheric drag that would cause the landing zone to be large. And previous missions have had landing zones up to 10 times larger than MSL. MSL is going to land in about a 20-kilometer across landing spot, and that allowed us to snug that up close to the very important sites that the scientists would like to explore. After we've completed that phase, we can dispense with the heat shield. We pull out the chute, the parachute. It's a similar chute design to previous Mars missions. And then we reach terminal velocity on the chute here. Then we start the engines, and we go into this powered descent mode here. And so that's our rocket pack that you saw in the previous picture in the assembly facility. This is the descent stage, and you see the rover tucked up underneath it. And when we zero out our descent velocity and horizontal velocity, we then lower the rover down on some cables, and then we touch that thing down to the surface, so directly on the mobility system, as you saw earlier. And that mobility system, of course, is well designed to drive around rocks and slopes on the surface, so it's actually a great landing system. And then when we're done, we remove those cables, and we send the descent stage over several hundred meters away to get it out of the way so it doesn't affect our chemical analysis equipment. And this will be a minimum of several hundred meters away. And then the rover is prepared to execute its surface mission by driving around. Now, the ability to drive a lot on the surface is important. Those of you who have been following Spirit and Opportunity know that, they've shown that driving a lot, driving many kilometers around the landing site allows you to explore a lot of different geologic settings and learn a lot about the history of where they've been on the surface. So we've taken that ability, which was kind of a bonus for Spirit and Opportunity, and built it into the baseline, the nominal mission for MSL. And as Don Sumner and John Grotzinger will describe, we actually intend to drive quite a bit, up to 20 kilometers or so at our final sites. Now, in terms of how to actually select a landing site, we have these capabilities of the rover, and we had science goals that the science community wanted us to explore. We had to take a look at each one of those sites and assess its safety. And we took advantage of a great asset, and that's the Mars Reconnaissance Orbiter, which has a high-resolution camera on board called HiRISE. And HiRISE, which on Mars could easily see this table if it was on the surface of Mars, we worked with the MRO project to basically take swaths, take strips of all of our sites, and do kind of a super Google Mars of all of our landing sites. So we had this kind of 1 meter resolution. We could see every rock that we could land on and every slope that we could land on, as well as, of course, doing scientific characterization of the sites. And these, on this graphic here, you can see the blue swaths indicate where those high-resolution images are. And in most cases, we actually have 2 images from different view angles, so I could actually make a 3-dimensional view of Mars and show the slopes very accurately. When we're completed with this analysis of what the characteristics of the terrain on Mars were, then let's go to the next graphic. We actually then built mock-ups of these surfaces and actually tested touching down the rover and driving the rover over all of those ranges of surfaces. So here's an animation where we actually dropped it on a slope, simulating a sloped surface, a sloped rocky surface on Mars. In some cases, we put boulders on the surface to see how the wheels would interact with that surface. This is an engineering copy of the rover, of course, not the flight one, so this one we weren't afraid to damage and to drop on rocks and slopes. And so we dropped it in all possible orientations of rocks. And when we were finished, our conclusion of this was that all 4 of those final science sites were safe for the mission to land on, and we could safely execute the surface mission. We could successfully navigate and drive to the targets and execute the science mission. And so at that point, we turned it back to the science committee and say, pick the best of the 4 from a science perspective. And that's really how you want these things to play out, right? You would love scientists to be able to go to the site that they want the most. And I think it's really a tribute to the engineering team that built a really beautiful rover here that's capable of accessing all of these great landing sites. Now, those 4 landing sites that were the finalists that we've talked about actually originated with dozens, over 50 sites, in a process that's played out over a 5-year period. And to talk about that process and the final 4 sites, I'd like to turn it over to my colleague John Grant from here at the museum.
Thank you very much. Well, 60 sites, 5 years, 150 scientists, toss in, as Michael described. Engineering doesn't become the discriminator on the final sites. And some of you might think that that's a recipe for chaos. In fact, it wasn't. In fact, the science community came together and worked very closely with the project and had very robust discussions that arrived at 4 terrific final 4 candidate sites. And what I'd like to do before I turn it over to Dawn and John to talk about Gale Crater is tell you a little bit about that process and remind you some of the attributes of these final 4 sites. So if I could go to the first graphic, please. What you'll be looking at is a map of Mars that has some shaded areas. The white shaded areas that you'll see to the north and south represent latitudes that are too far to the north and south for Mars Science Laboratory to land. You'll also see an area that's blacked out through the middle, and those are areas where the surface of Mars is too high for MSL to land. So there's a variety of colored terrain there that represents the targets, the potential targets for MSL to go and try to evaluate the habitability of Mars. And the red dots that you see represent the 60 locations that were proposed by science team members, by the science community, and evaluated during these workshops. The 4 blue dots that you see there, Eberswalde, Gale, Holden, and Marth, represent the 4 candidate sites. And I want to tell you a little bit about why those represent terrific final candidate sites. If I could go to the next graphic, please. These show you little snippets for each of the 4 sites. Eberswalde in the top left, Gale crater to the right, Holden crater to the bottom left, and Marth Vallis to the lower right. Why do these represent great sites? Well, in Eberswalde crater, you land at what's perhaps the best delta on Mars. This is an incredible system of drainage into a crater that was probably filled by water, standing body of water that accumulated deposit, much like you would see at a river delta on the Earth. In Gale crater, as you've heard from Michael, there is this enormous stack, 5 kilometers thick of layered material, which represents the opportunity to literally read chapters in a book of the history of past deposition on Mars. For Holden crater, you've got a system of dry rivers, much like you see flanking the edges of Death Valley in California, that drain down into a deposit of finely layered materials, which probably represent an ancient lake bed. So one of the most diverse river lake systems on Mars. And in Marth Vallis, you've got an incredibly detailed system of iron-rich and aluminum-rich clays that are layered and occur in a regional setting that represent a long history of ancient water interaction, and is probably the oldest of the 4 sites. So as John Grotzinger is fond of saying, these are sort of like different flavors of ice cream. All fantastic, but slightly different twists on that general take. Let me give you a couple of examples of the details of what we might have gone to look at with the next graphic. So for Eberswalde crater, as I mentioned, the best delta on Mars, well, you can see on the left here, and all the scale bars that you see here are in kilometers. The crater is represented, the colors represent low is blue and purple, high is yellow and red. The landing ellipse is shown there on the left, and the yellow box that you see represents a potential science target outside of the ellipse. The white box represents one within the ellipse. So all 4 sites represent a variety of high-value science targets within and around the ellipse. Outside of the ellipse in Eberswalde, you can see these scrolls that are produced as the drainage system came down and deposited the delta, much like we see on Earth, much like the places on Earth where we go to look for accumulated organic materials. Further out into the ellipse, we see older riverbeds and lake beds that would be explored on the way to the delta, providing us with a view of a setting on Earth that we're very familiar with. If we go to Gale crater with the next graphic, please. We see the landing ellipse is just to the north of this large mound of material. We would land on an alluvial fan, which represents material shed off the walls of the crater, this ancient crater recording ancient conditions, ancient processes on Mars. And then we would traverse to the south and access through a Grand Canyon-like gap into the wall of this mountain of material, these finely layered sediments that allow us to go up and read the changing environmental conditions that have occurred through time. And then if we think about Holden crater, the next graphic, please. As I mentioned, this diverse river and lake system, we would land and access these dry alluvial systems, alluvial meaning much like the kinds of drainages that you see in Death Valley. Through craters, we can see the kinds of sediments that have been transported and reconstruct the environmental conditions, but ultimately access these finely layered materials that are further out on the floor of the crater and decide whether or not there was an ancient lake on the floor that could have accumulated the materials that might allow us to evaluate habitability. And then finally, with the last graphic, Marth Vallis. This is in the northern hemisphere. It lies between Marth Vallis to the east and Oyama crater to the west. Both within and outside the landing ellipse, there's this incredibly detailed stratigraphy of iron-rich and aluminum-rich clays that represents sort of a regional deposit. It's an incredibly ancient deposit and records something fundamental about the early interaction of water on Mars with those rocks and tells us something about ancient habitability. So I hope I've told you that all 4 of the final candidate sites represent an incredible opportunity for MSL. And as Michael and Michael pointed out, it was a very difficult decision to arrive at a final one. I will now let Don Sumner tell you a little bit about Gale crater and why it ended up being the eventual landing site.
So I had the joy of co-chairing the project's landing site working group, and we spent hundreds of hours discussing the sites, doing analysis of the sites, and trying to come up with the best science that we can do with the MSL payload. There are lots of flavors of ice cream, and we have certain ways to investigate those. And the project scientists and NASA felt like Gale was the best match for the goals of the mission, evaluating habitability, and also for the instrumentation that we have for MSL. So if we could get the first graphic. I'm just going to show a fly through into Gale crater and give you a sense of what an incredible place it is geologically. So we'll land in a landing ellipse, which is in the flat part towards us from the mound in the view that you see now. And within that, the landing ellipse, there's material shed off the crater wall that will give us a chance to look at what the Mars crust is like. That material was moved by water, those rocks were transported by water, and that water either infiltrated into the ground or evaporated. And so there's also a unit that's very hard and dense that we're wondering about how it reflects that change of environment. So this is the youngest environment we'll look at with MSL. One of the fantastic things about this rover that Mike talked about is that we can go a long ways. And this allows us to rove towards places where the rocks are better exposed. Geologists like climbing up cliffs, and we get to go to those places with this rover for the first time on Mars. So the area of most scientific interest in Gale is at the base of the mountain, which we're zooming into here. And there we see mineral signatures of clays and also sulfate salts. And both of those are key classes of minerals that tell us about the environment on Mars and the interaction of water with that environment. And water is critical to habitability. So the rover will go towards the mountain. There are layers that we hope to see variations in this mineral that will tell us about how those minerals formed, how the environment changed through time. And based on the signatures from the orbital instruments, we expect to find variations in those minerals, and particularly in the sulfate salts, which will tell us about the water, how concentrated it was, whether it evaporated, the sources of the water. And that will give us a history of some of the ancient environments on Mars, how those changed, and help us evaluate the habitability of the planet. Those sulfate salts also contain water in them, and when they heat up, they release that water, and when they cool down, they can absorb the water. And so we have a great instrument package to look at how the water in those salts is exchanging with the modern Martian atmosphere, and it will give us a better sense of the water cycle on Mars, which has been very difficult to evaluate. Now, there is also, after the deposition of all these layers recording the environment, we had a time when you had water flowing down the mountain of Mars, and that cut a canyon a lot like the Grand Canyon. So that gives us the opportunity to read the environments through time and those changes, but that canyon cutting event also represents an environment that could have been habitable, where you have the flowing water, you have erosion, and you have deposition of those sediments at the mouth of the canyon, which is at the front view of the video here. And so the sort of suite of things that we can see at Gale represent a diverse number of environments over a long period of time, possibly tens to hundreds of millions of years, plus the modern environment. And so the Gale site represents just an incredibly rich suite of scientific investigations that we can do. And it's also just going to be an incredibly beautiful place. It will be a lot like a lot of the southwest areas like Monument Valley, where we have these steep-sided cliffs with the rover going in the shallower valleys between them. And we have the incredible instrumentation to characterize the texture and shapes of the cliffs and the mobility to travel through this area. So the science at Gale is going to be amazing, and it's going to be a beautiful site to visit. And John will tell us more about how we'll actually use the instrumentation to make some of these investigations.
Great, thanks very much, Dawn. So what I'd like to talk to you now about is the way that Curiosity is going to explore the Gale landing site. But let me drop back to a minute to try to reinforce to you what an amazing precedent is being set right now with the MSL mission. As Mike talked about, one of the things that became obvious to the science team members in the community, and John said there was about 150 that attended these workshops. Our science team has 263 science team members at this time. And by the time that students are added to this, and postdocs and people like that, and participating scientists, we're likely to swell to 300 team members. What we saw happening was the unexpected possible outcome that we may be left with four landing sites, any of which might be chosen as the final landing site, that engineering would not kick one or more of them out. And that's what's always happened in previous missions. So we began to think about this in the project and how in the world we were eventually going to come together with headquarters and arrive at this decision. And as Michael said, it was not easy. Here's why. This metaphor of thinking about ice cream, it's a hot day. If any four of you go out afterwards and decide to go out and get ice cream, I'll bet you will not all get the same thing. And if somebody asks you why you choose between vanilla and chocolate, you're just going to say, well, it tastes good. It's what I prefer. And when you come down to four landing sites, that's basically what it comes down to. Which one feels right? And so in the end, there's no hard yes or no answer. You don't make a long list of things and put numbers by them and add them up and figure out what goes on. So we as a science team, as a community, we got together, and in the end, we picked the one that felt best. And so why does it feel good? Well, as Dawn was explaining, you've got a mountain of rocks that's 5 kilometers high. That's higher than the tallest mountain in the lower 48. It's taller than Mount Whitney. It looks like Hawaii. If you come sailing up to Hawaii, the thing about this mountain is that it's not a tall spire, it's a broad, low, mound-like shape. What that means, we can drive up it with a rover. So this might be the tallest mountain anywhere in the solar system that we could actually climb with a rover. So we think and plan around a 2-year mission, but we have a hope that if we lived longer, we might be able to keep going higher and higher up that mountain. That alone, it justifies sending the spacecraft there. Then when you start adding in the science goals that are on top of it, it turns out that the most attractive targets are at the base of the mountain, and we have a payload that we can address those with. So in the 2 years that we have to run this mission before the warranty expires, we can address the principal goals, which are the kinds of things that the Mars community would really like answers to. So what you can see in the first graphic that we have up there is the spacecraft with all the instruments that are on. And we have 9 principal investigators that have contributed instruments that are now part of the rover, which is down at Cape Canaveral. And those principal investigators are Dave Blake, Ken Edgett, Javier Gomez Elvira, Ralph Gellert, Don Hassler, Mike Malin, Paul Mahaffey, Igor Mitrofanov, and Roger Wiens. And they have built 10 instruments that sit on the rover. And if I just describe a few of them, we can start off with everybody's favorite, which are the cameras. On MSL, we have 17 cameras. You all are going to get lots of pictures to look at. There's a camera that's mounted to the bottom of the rover, and in the video that Mike showed you where the sky crane is reeling down the rover, this camera is going to turn on. It's going to take a movie at 5 frames per second, full color, HD resolution. That'll be one of the most spectacular public outreach data products that's ever been created. We have cameras that are up on top of the mast that we can use to look around and try to find the types of rocks that we would like to do chemical analysis on. And when we think that something is particularly promising, we can drive up closer, and then we have a laser that shoots out in front of the rover up to a distance of 7 meters away that zaps the rock, creates a spark of light, and then we look at that spark, and based on the light content, it tells us about what chemical elements are in the rock, and are they the kind of chemical elements that are consistent with a habitable environment. And then if so, we drive over to the rock, and then we take the arm, we deploy the arm, we put it down on top of the rock, and we have a drill This is just like a drill that you buy at Home Depot. The drill goes into the rock up to 5 centimeters, creates a powder. The arm then collects the powder, brings it back, takes it on top, drops it down into one of these holes on the top of the rover, and we have 2 instruments that are inside the rover there. And what you can see in those instruments is the mineralogic composition of what's down there on Mars. So we hear about all these hydrated minerals that we see from orbit, and now we're going to be able to really determine the composition of those minerals. And in addition to that, we can also take a look for organic carbon. Now let me emphasize that we are not a life detection mission, and we cannot look for fossils, microbial fossils of any type. But we can look potentially for organic carbon that might be preserved there. Our primary goal in this mission is to explore habitable environment. And that means we had water present. That means we had a source of energy for microbes to undertake metabolism, to live. And then we also have a source of carbon for life as we know it. But here's the trick. If we want to look for organic carbon, we have to be able to work with rocks that look much like this one does. This is a rock that comes from the early Earth. It's almost 3 billion years old. And it tells us a lot about the early environmental evolution of Earth, particularly the rise of oxygen on Earth. And these layers that you see here are the things that we're interested in. This rock started out as sedimentary particles. And those sedimentary particles may have been associated with organic matter. But here's the problem. When the sediment becomes a hard rock, all that organic matter can be destroyed. So this is a very, very difficult challenge that we have for us. On a planet that teems with life, on Earth, we almost never see organic carbon preserved. But it does happen. And so we hope to be able to look for organic carbon. That's what we can hope for. What we can promise to deliver with MSL is an understanding of the environmental history of Mars. Okay, so if we go to the next one, what we can see in this slide now is the rover itself. Mike's already showed a picture of this. You can see all the instruments that we've been through before. So I'd like to skip on to the next one. And what you can see here is where we'll land in the images that Dawn was showing. Right in the center of the ellipse, we have something that looks like one of these water lane deposits. It's called an alluvial fan. We think that water was flowing along and transporting sediment particles. And then out in front of it, in the blue outline, we have this very hard rock that Dawn was talking about. We don't know how this is formed. It's a big mystery to us, but it looks very special. And it's one of the things that uniquely goes along with the Gale site. Then we can drive out of the ellipse and go up to where it says clays, which is one of the types of minerals that's associated with water. It formed in an aqueous environment. And that patch of green there is a place that we would study. And then we go up into where it says sulfates. That's another kind of a hydrated mineral. And then we work our way up the mound. So what we're doing is we're exploring a geological environment that consists of a stack of layers that tell us about the environment. So now let me skip to the next one. And why do these layers matter? Well, this is the history of geological exploration on Earth. And 150 years ago, when the first explorers went down the Colorado River and discovered the Grand Canyon, they saw all these layers of rocks. And what we have learned from 150 years of exploration is that if you start at the bottom of the pile of layers and you go to the top, it's like reading a novel. And we think Gale Crater is going to be a great novel about the early environmental evolution of Mars that offers strong prospects, potentially, for the discovery of habitable environments, and maybe even a shot at potentially discovering organic compounds. But even if we don't find those organics, what we learned from studying a place like the Grand Canyon is the way that the environmental history and habitable environments changed on Earth, and we think we're going to get that for Gale. So let me finish with the last one. This is what our book is going to look like as we go up through the mound. We're going to start out, the first chapter is going to be what we've got in the landing ellipse, which looks pretty darn exciting already. And then we're going to head out of the landing ellipse and go towards that green star, and that's where the clay minerals are forming the layers. And then after we're done with those, we're going to head up into the third chapter and look at these sulfates where the yellow star is. And then after we're done with that, we can go up to the top, and now we've gone through hundreds and hundreds of meters. And just for reference, with the Opportunity rover, we've been working 7 years, we've gone through about 20 meters of rock. What we see here in this image is hundreds of meters of rock. So we have that many more pages to read in this book of the early environmental history of Mars. And just one thing that, in addition to these minerals that we can see from orbit that gives us a lot of excitement for this site is in the next slide. The blue star is a feature that we can see from orbit that's been published, observed elsewhere on Mars by the HiRISE team led by Alfred McEwen. We see these fracture systems. They occur all over Mars, and in some places they are spectacularly developed. Gale crater is one of them. And they're not down at the bottom of the mound. They're developed hundreds of meters up into that story about the environmental evolution. And what we see, the fracture that blue star is on, if you look at that thing, it makes a line, and notice that there's a dark line right in the middle. On either side, there's two white lines. Those two white lines tell us that that was likely an open space in which there was water that filled in with minerals, and that's the kind of thing that we think is a very bright prospect for a habitable environment. So to summarize, we have many attractive possibilities at Gale. We think it has exceptionally high diversity for different kinds of habitable environments, and it is possible that some of those might preserve organic carbon. So with that, I'll turn it back to Dwayne.
Thank you. I'd like to ask the media who are attending here if they can make their way to the microphone if they have questions, and then we'll go to the phone line. I would like to remind folks out there watching this program that you can find all of this information on www.nasa.gov/MSL. And for folks out there who have Google Earth, an incredible Google Mars component to that, check that out. And I think it's certainly appropriate not only to give a round of applause again to the folks up here, but also to all of the folks across this great country and worldwide that are working on this mission, and particularly the folks at the Kennedy Space Center who are going to take us back to Mars, ladies and gentlemen. Okay, let's go to the phone line here with Irene with Reuters. Irene? We'll come back here. Go ahead, Eric. You should give your name and affiliation.
Some people on your science team are saying that this could even be a bathtub that was once filled all the way to the top with water. Others are worried that maybe some of these watery signs could just be carried in, almost as a layer of dust by wind. What's your best estimate for how much water was once in Gale crater, and can you describe some of the ways in which it would have gotten there?
There is when we're going to begin to get answers to these questions that you're asking. And right now what we've got are hypotheses, and so the way that we can go about testing them is using the payload to make particular estimates of the environments that water may have been present in. And what I would say, the most important thing that we need to be left with is to make sure that in the year that we arrive at the Gale landing site, we can continue to refine our hypotheses and come up with particular observations that we would make. And I think the most important thing is the question of how much water may have been there. There may not be one answer. There could be multiple answers. The reason that Gale is attractive is because there's likely to be multiple scenarios in which water would have been present, but at this time we just don't know how much would have been there.
Space Magazine. I don't know if you can go back a couple of slides to that whole stratigraphy that you were showing, but have you started to map out how you actually climb the mountain? I mean, to the first order of, that's a 3-mile high mountain. I mean,
yeah.
And I realize the relief has been exaggerated there, but.
Yeah, it's a 3 times vertical exaggeration. And we are committing only to climbing the lower part of the mountain. And in the project, one of the things that we did to confirm this site as being viable from an engineering perspective was we conducted a study by a subset of people on the team and within the project called the Gale Summit Team, and they were charged with the responsibility of making sure that we could actually drive there. So Mike and I got together with some of the engineers and a handful of scientists to try to drive this terrain, because now, don't forget, this HiRISE camera is incredibly valuable because you can see this table from orbit. And so that means we could come up with accurate models in advance of arriving there and drive them across the terrain and make sure we can do it. So we had multiple paths that we found that we can get us up through those layers.
Okay. And if you were to get all the way to the summit, can you even guess at how long that would take? The full year?
No. I think basically where the blue star is, that would probably take us 2 years to get there. And then after that, as I said, the warranty expires. But if history is a predictor of the future, we expect to have, some future life left to go. But if we were to go on for 10 years, we think we could just keep climbing. It's going to take years to get to the top if it's possible.
One of the issues with how fast we go is how long we spend on the scientific investigations. So it's not just a matter of the engineering capability of driving, it's the fact that there's a sort of rich suite of things to look at. And so there's a balance between characterizing where you're at and going to see the next thing. And that'll be a very exciting part of the mission.
And one last one, can you say how steep a slope this can climb and compare that to Spirit and Opportunity?
Mike, you
in some ways it's similar. I think we probably will generally be climbing slopes around 20 degrees or so. And that's similar in slope capability in terms of traverse to Spirit and Opportunity. It has similar ground pressure, and so you probably expect it to be able to negotiate slopes that are similar to what we've seen for Columbia Hills or some of the crater entries.
Thanks.
Okay, we're going to take one more question, then we'll go to the phones and try to come back and wrap up. So good.
Suzanne Presto from VOA. I had a similar question about time frame and how quickly will you be getting information back from this mission, and also given that Opportunity and Spirit have been going years beyond, do you really think that this could be going for 10 years and beyond that possibly?
We'll see what happens. We have planned for a 2-year mission. The 2-year mission, we understand that we can achieve the principal science goals that we observe and create hypotheses about there. And after that, we'll just have to see. But the point that Dawn was making is a good one. If we land and find something that's so incredibly interesting that we want to spend 6 months there, we probably will. So there's no requirement on this mission to drill a certain number of samples, analyze a number of rocks, drive a certain number of kilometers. We are really in the phase now where we are doing true scientific exploration, and we'll test hypotheses, and when we're satisfied, we'll move on. But that said, our hope is that, our plan going into this is that we will move through some targets in the landing ellipse, and we do want to get to the base of that mound. That is our target for the mission.
Okay, let's go back to the phone. And Irene?
Hi, thanks very much. Can you hear me all right?
Yes, go ahead.
Hi, thanks. I had 2 questions. The first is, if someone could maybe just talk a little bit about what the deciding factor was in giving Gale the edge over Eberswalde, which I believe was kind of tied for the top slot.
I'll take one crack at it. Essentially, it really was flavors of ice cream. It was very difficult. And so one of the things that we did was we had a meeting of the Mars Science Laboratory science team. So this is the principal investigators and all the co-investigators involved in the mission, and basically just did a vote. And we ended up with 2 front runners, Eberswalde crater and Gale crater. And then, but there's a slight preference for Gale. And as there was more discussion and also asking the PIs themselves, the 9 people who built the 10 instruments, there was a real preference for Gale in that it's not a one-trick pony. As we saw from this talks today, that there's several different environmental settings that can be explored, any one of which might have the possibility of preserving some organics. So you don't have to have the scientific hubris of thinking that you know exactly where to go or what mineral to target. You actually have the choice of several different things, so that if one doesn't work, perhaps the other one gives you the great payoff.
Okay. Ladies and gentlemen, I'm going to have to jump in here. We are, unfortunately, out of time. This room has to be reconfigured for the Mars Day, but I would like to tell the media who are sitting here and the folks on the phone that these folks will be available. We will make them available following this press conference, and I want to thank you all for joining us. We want to thank the museum for hosting us, and when it comes to Mars, science never sleeps. Thank you.